This week we will study evaluating limits algebraically. The objectives of this section are to find limits using direct substitution and find limits when substitution doesn't work. There are two properties of limits that we're going to need in the covering of this section. One of them is limits of polynomial functions. If p of x is a polynomial function and c is a real number, then the limit of the polynomial function p of x when dx get close to c is equals to p of c. So we evaluate the function at the value c. And the other one is limits of rational functions. If r of x is a rational function defined by p of x over q of x, then the limit when dx get close to c of r of x is equals to r of c equals to p of c over q of c, with the condition that q of c has to be different from 0. So same as with the limits of polynomial functions, to find the limits, what we do is to replace the value of c into the rational function r of x. Here we have an important fact. The limit, if it exists, of a function f of x as the x get close to c is f of c if f of x is continuous at the value c. This is direct substitution. Here we have an example, a graphic example of a continuous function, and we're going to evaluate this curve of this function at 2. F of x is continuous at x equals 2. So f of 2 exists in the limit when the x get close to 2 of f of x equals to f of 2. So we find the value of the function f at 2, and we notice that f of 2, by looking at the curve at the graph, it is 4. Therefore, f of 2 equals 4. And here we have the first example of direct substitution, and we're going to find the limit if it exists. So here we have a polynomial function, and what we need to do is to find the limit of 2x cubed plus 1 when the x get close to 3. And this is really simple. The only thing that we're going to do is to replace the x by 3, and this becomes 2 times 3 to the third power plus 1. This is equals to 2 times 27 plus 1, and the answer finally is 55. So this is a continuous function, and when it is continuous function and we need to find the limits, what we do is to substitute directly the value that the function is getting close to. So we have a second example of direct substitution. We're going to find the limit if it exists of the function x squared minus x plus 1 when the x gets close to 2. So this is a polynomial function. We just substitute directly the value of the x, that is 2. This is equals to the second power minus 2 plus 1. Simplifying, it becomes 4 minus 2 plus 1, and our final answer is 3. Okay, and here we have an important idea of the way that we're going to find limits. The limit, if it exists, of f of x as x get close to c is not f of c if f of x is discontinuous at c, and in this case we cannot use substitution, so we must be able to apply other techniques. If substitution results in an expression a divided by 0, and where the value of the a is different from 0, the limit does not exist. When the substitution technique results in a 0 over 0 fraction, the result is called an indeterminate form, and we're going to learn how to deal with these indeterminate forms when evaluating limits. So here we have the factored in cancellation technique, and here we have the procedure to complete this process. In 1, we're going to try substitution like we did before. In 2, we're going to factor and cancel if substitution doesn't work. In 3, we're going to try substitution again. So this is the way that we find a limit, by using factoring and cancellation technique. let's make an example where we can see how the factoring works for finding limits. Find the limit if it exists of the expression x minus 2 over x squared minus 4 when the x value gets close to 2. So direct substitution works. Let's see. Let's replace the x by the value 2. So direct substitution, so it will be at the top, it will be 2 minus 2 over, replacing the x at the bottom, 2 to the second power minus 4. And in both cases, top and bottom, we get 0, and we have the form 0 over 0, that is an indeterminate form. So direct substitution doesn't work. So let's see if we can use factoring to find the limit. So the limit when the x gets close to 2 of the expression x minus 2 over x squared minus 4 becomes x minus 2 in the top, and in the bottom we can factor x squared minus 4 as differences of 2 squares. So we have the expression x minus 2x plus 2 at the bottom. So this is equals we can notice that we can in here cancel the factors at the top and the factors at the bottom. So the limit of x when this expression when the x gets close to 2 becomes equals, after we cancel x minus 2 from the top and the bottom, 1 over x plus 2. And if you notice, at this point we can use direct substitution again. So we replace, and we won't get a 0 in the denominator, so we replace the value dx by 2 in this expression, 1 over x plus 2, and what we get is 1 over 2 plus 2, and the answer would be 1 over 4. Therefore, the limit when the x gets close to 2 of x minus 2 over x squared minus 4 is equals 1 over 4. And the way that we solved this, it wasn't by direct substitution at the beginning, it was by using factoring, and then at the end, once we cancel those factors and make the denominator 0, we can use direct substitution, and we can find a value that it makes sense, or at least that we were expecting as an answer. Let's make another example. Let's find the limit if it exists of the expression x cubed plus 1 over x plus 1 when the x gets close to negative 1. So let's see substitution. Let's see if substitution works. Let's do it mentally. Negative 1 to the third power would be negative 1 plus 1. Negative 1 plus 1, it would be 0 at the top. And at the bottom, negative 1 plus 1, it would be also 0. So 0 divided by 0, we get an indeterminate form, so it doesn't work. So does this mean that the limit does not exist? Let's check. Let's try factoring in the cancellation technique. So in here, the question is, how can I find the limit when the x gets close to negative 1 of the expression x cubed plus 1 over x plus 1? So if you notice, the expression x cubed plus 1 at the top is a sum of cubes. And we have a special factoring technique for a sum of cubes. When we have a cubed plus b cubed, this is equal the following. We take the cubic root of a cubed and b cubed. Cubic root of a cubed is a, and the cubic root of b cubed will be b. So we enclose these expressions in parentheses by using the plus sign, a plus b times, and the factoring is completed like this. We raise the a to the second power, so we get a squared, minus, is the term in the middle, in the second parenthesis, minus the product of a and b, so it will be minus ab, and finally plus the square root of the second term in the first parenthesis plus b to the second power. And this will be the way of factoring a cubed plus b cubed. So let's see how we can apply this to the expression that we have. This limit becomes equals to the expression at the top, factoring x cubed plus 1, it will be the cubic root of x cubed is x, so we put that in the first parenthesis, x plus the cubic root of 1, that is 1, so we put that expression also in the first parenthesis, so we get x plus 1 times. How do we get the second parenthesis? What we do is to raise the x to the second power, so we get x squared, minus, it is fixed, the product of x and 1, x times 1 is x, so it will be minus x plus the square root of 1, so 1 to the second power, it will be 1. So the expression at the top becomes, after we factored the x cubed plus 1 expression, equals to x plus 1 over x times x squared minus x plus 1. And at the bottom, the x plus 1 expression, we just leave it like that. And what we can do next, what I notice in here, is that x plus 1 at the top with the x plus 1 at the bottom can be cancelled. And now the limit becomes equals to the expression of x squared minus x plus 1. So the limit becomes limit when the x gets close to negative 1 of x squared minus x plus 1. And at this point, notice that the denominator is like the denominator cancel, so we don't have a fraction anymore. And at this point, we can use direct substitution. So we replace the x by negative 1 and wherever we see the x. So negative 1 to the second power minus negative 1 plus 1 becomes negative 1 to the second power is 1, negative times negative is positive, plus 1 plus 1, so the answer is 3. Therefore, the limit when the x gets close negative 1 of x cubed plus 1 over x plus 1 equals 3. I want you to try to find this limit when the x get close to 3 of x squared minus x minus 6 over x minus 3. See if the direct substitution works. So in case you notice that you get a determinant at the top and at the bottom, or you get 0 at the bottom, so it means that the direct substitution is not going to work. And what you need to do next is to see if you can factor the top, x squared minus x minus 6. It looks factorable. It looks like a guessing a trinomial that you can use guessing. So try to factor it to see if something can cancel with the bottom. And after that, when you cancel some expression at the top with the bottom, you're ready to use direct substitution, check, and the answer that you must get after you try all this that I mentioned, the answer must be equals 5. Let's make a new example. Let's find the limit if it exists of the expression square root of x minus 2 over x minus 4 if the x get close to 4. Let's see if we can use direct substitution. If we replace the x by 4, top and bottom, what we get is the following. Square root of 4 minus 2 over 4 minus 4. The square root of 4, it is 2 minus 2 will be 0 on the top, and 4 minus 4 at the bottom, it will be 0. So 0 divided by 0, it doesn't work. So in here we get substitution, doesn't work, and we get an indeterminate form, so it doesn't work. Let's see the factoring canceling technique works. It's obvious that the square root of x minus 2 is not factorable. You cannot use any factoring technique. The same happens with x minus 4. So the factoring canceling technique doesn't work. So what we can do in this case, is to rationalize. We can rationalize the numerator, and this is going to allow us to factor and cancel and then use substitution. So let's see what does it mean rationalization. Here we have the same example as before, that we proved that it's not possible to use substitution or factoring and canceling technique, so it doesn't work. So the recommended technique was to rationalize. So what we're going to do to rationalize is to multiply top and bottom by the conjugate of the expression at the top, square root of x minus 2, in the conjugate of square root of x minus 2, it will be the square root of x plus 2. So the only thing that we do to get the conjugate is to switch the sign in between. So we multiply that expression, the limit given by square root of x plus 2 over x square root of x plus 2. And when we simplify this, what we notice is the following. If I multiply at the top square root of x minus 2 times square root of x plus 2, I notice that the only difference between them is the sign. So this is like having a minus b times a plus b. So when we have that, we can use a special product, a minus b times a plus b equals a squared minus b squared. Therefore, the square root of x times the square root of x, it will be square root of x squared, or just x minus 2 times 2 will be 4. And at the bottom, there's nothing to do more than leaving the product indicated, and it will be x minus 4 times square root of x plus 2. So this is what we get. Limit when the x get close to 4 of x minus 4, because we multiply by using the special product at the top, over nothing to do at the bottom, x minus 4 times square root of x plus 2. And I notice that at this point I can cancel the factors x minus 4 and x minus 4, and this becomes equals the limit when the x gets close to 4 of 1 over square root of x plus 2. And at this point, what I can do is to substitute. Once I cancel factors in common, I can replace the 4, and I won't get a 0 in the denominator, so this becomes equals 1 over square root of 4 plus 2, square root of 4, that is 2, 1 over 2 plus 2, that is equals 1 over 4. Therefore, the limit when the x gets close to 4 of the square root of x minus 2 over x minus 4 exists, and it is equals 1/4. Let's see a new example. Here we have to find the limit. We need to find the limit of the expression square root of x plus 1 minus 1 over x when the x get close 0. So again, we try substitution. You replace the 0 by the x by 0 will be 0 plus 1. It will be 1, square root of 1 is 1, minus 1 it will be 0, over replacing the x also by 0 will be 0 over 0. So again, substitution doesn't work because we get an indeterminate expression. And what if we try to factor in canceling? It is impossible to factor square root of x plus 1 minus 1, and also we cannot factor a monomial if that is x at the denominator. So it doesn't work. And again, what we're going to do is to rationalize, and we're going to rationalize the numerator to factor and cancel, and then do the same that we did before, substitute. So in here, we have the same exercise, and like we said before, what we're going to do is to rationalize. So we're going to multiply again by the conjugate of the expression that contains a radical. And I see that the radical is at the top, so we're going to multiply by the conjugate of the square root of x plus 1 minus 1. And the conjugate is going to be square root of x plus 1 plus 1. So we're going to multiply and divide by that expression. So we have this expression, and I'm going to use a special product, a minus b times a plus b equals a squared minus b squared. And in this case, a is the square root of x plus 1 and b is 1. So when I multiply, or when I apply the special product, and I simplify square root of x plus 1 to the second power on those, the radical symbol stays only x plus 1, minus 1 to the second power, so remains only 1, so minus 1. And at the bottom, as before, is nothing to do, just to leave the product indicated. So here we have what we just mentioned before. It would be the square root of at the top of apply the special product of x square root of x plus 1 to the second power minus 1, and at the bottom we just leave the product indicated. Once we use this, we simplify the radical with the power 2 in the expression square root of x plus 1 to the second power, the radical in the power disappears, and the expression becomes limit when the x gets close to 0 of x plus 1 minus 1 over x times square root of x plus 1 plus 1. So 1 minus 1 cancels, it's only left the x. So the limit when the x is close to 0 of the expression, now the expression is x over x times square root of x plus 1 plus 1. And did you notice we can cancel the x at the top with the x at the bottom, and now the expression becomes limit when the x gets close to 0 of 1 over the square root of x plus 1 plus 1. And at this point, now we are allowed to make a substitution. We replace the x by 0, and the expression becomes the limit when the x gets close to 1 to 0 of square root of 0 plus 1 over the square root of 0 plus 1 plus 1. 0 plus 1 is 1, square root of 1 is 1 at the bottom, and 1 plus 1 is 2 at the bottom, so the expression becomes equals, the limit equals 1/2. Therefore, the limit when the x gets close to 0 of the expression square root of x plus 1 minus 1 over x equals 1/2. Now try to find the limit of this expression on your own. The limit when the x gets close to 0 of the expression square root of 2 plus x minus square root of 2 over x. So in this one, the direct substitution is not going to work. Factoring and canceling technique is not going to work. So what you need to do is to rationalize the numerator. And the answer that you do all the process must be 1 over 2 square root of 2. And here we have some special limits at infinity. What happens when a function gets close to infinity or goes to infinity? So here we have 3 special limits that we need to know for in order to simplify the exercise that comes. The limit when the x goes to positive or negative infinity of a constant, it is equals to the constant. So it makes sense when you try to replace the x by a really big number or a really small number that goes to positive infinity or negative infinity, and what you are evaluating is a constant, it's nothing to evaluate, so the answer would be the constant. And the next one, when the limit gets close to negative infinity of 1 over x, or when the limit when it goes to the x goes to positive infinity of the expression 1 over x to positive infinity, what happens? What is the limit in both cases? So think of this. If you divide 1 by a really small number, like negative 1,000, negative 2,000, negative 3,000, negative 1 million, or when you divide by a really large value like 1,000, 10,000, the answer in all those cases is going to be 0. So the limit when the x gets close to negative infinity, 1 over x, or when the x gets close to positive infinity, 1 over x, the answer is going to be 0. And the third one, something similar happens when the x gets close to positive or negative infinity of an expression like 1 over x to the n. So this power x, the expression at the bottom, x to the n, becomes even more larger than the previous one. It's obvious that the limit when the x gets close to positive or negative infinity of an expression like 1 over x to the n is 0. So this number, the number that you're obtaining when the x increases or decreases, it's going to be 0. Let's make an example where we can apply what we just see. So let's find the limit of a rational function at infinity. Let's find the limits of the expression 3x plus 5 over 6x minus 8 when the x goes to positive infinity. So what we're going to do in here, pay attention to this, is to divide each term by the highest powered term. So here I notice that the expression with that has the x at 3x and 6x, so both expressions have the x, so the greatest power in here is x to the 1. So what we're going to do in the next step is to divide each term, top and bottom, by x. So this becomes limit when the x gets close to positive infinity of 3x divided by x plus 5 divided by x over 6x divided by x plus 8 divided by x. So each term was divided by the highest power term. And this becomes, simplifying, equals to the limit when the x gets close to infinity. 3x divided by x, it will be 3, the x is cancelled. Plus 5 over x is nothing to cancel, so I leave it like that. Over 6x divided by x, the x cancels, so we get 6 minus 8 divided by x is nothing that I can simplify. So in the next step, I'm going to apply the limit to every single expression. I'm going to find the limit of 3, of 5 plus x, of 5 over x, of 6, and 8 over x. And I'm going to apply this rule. The limit when the x gets close to positive infinity of 1 over x, remember, is 0. As the x increases, 1 over x goes to 0. So let me take the limit, like I said, of each of the terms. So limit when the x gets close to positive infinity of 3 plus the limit when the x gets close to positive infinity of 5 over x over the limit when the x goes to positive infinity of 6 minus the limit when the x gets close to 0 of 8 over x. And this becomes equals. We're going to simplify this. The limit when the x gets close to positive infinity of a constant, in this case 3, is 3, plus I can decompose 5 over x like 5 times 1 over x. So I said plus 5 times. What will be the limit of when the x gets close to positive infinity of 1 over x? Remember that we have a property that is equal to 0. So 5 times 0 over. What is the limit when the x goes to positive infinity of 6? It's a constant, so it remains as a constant. 6 minus, I do the same with the 8 over x, is the same as 8 times 1 over x. So I can say minus 8 times the limit when the x gets close to positive infinity of 1 over x, and that limit is 0, so times 0. Then I simplify this expression, 3 plus 5 times 0, 5 times 0, plus 3 will be 3, over 6 minus 8 times 0 will be 8 times 0 is 0, so 6 minus 0 is 6, 3 over 6, and 3 over 6 is 1/2. And now try to complete the following limits. Let's find the limit, if it exists, of the expression for x squared minus 6 over 2x cubed minus 5 when the x gets close negative infinity. Remember that you have to divide each of the terms by the highest power term. That in this case, I don't know, you see that the highest power term that I see here is x cubed. So what you need to do is to divide each term by x cubed, and then simplify as we did in the previous exercise to see what is the answer. And if everything goes correctly, the answer must be, the answer that you get is going to be equals to this value, 0. And this is the end of this video. Thanks for watching. Thanks for being patient to listen to everything that we have to say to every one of you. And I hope that everything has been understood. And in case you have any questions, we can answer those in the next Zoom meeting.